Our galaxy is over 100,000 light-years across, a distance so vast it defies ordinary understanding. Even humanity's earliest radio signals, traveling at the speed of light, have barely reached a fraction of it. So how did we, tiny beings on a blue planet, figure out where we are in all this? For most of recorded history, humans believed they were at the center of it all. The Earth wasn't just home. It was the anchor point of the cosmos. To ancient observers, this idea felt intuitive. Every day, the sun rose in the east and set in the west. The stars rotated around the night sky in perfect, predictable patterns. Planets wandered in elegant loops. From our limited viewpoint, it looked like everything was moving around us. This geocentric model, most famously formalized by the Greek astronomer Ptolemy in the 2nd century, held sway for nearly 1,500 years. According to this model, Earth was fixed and motionless, and the heavens turned around it in crystalline spheres. And honestly, who could blame them? With no telescopes and no understanding of gravity or planetary motion, early thinkers built models that fit what they could see. It wasn't arrogance, it was just the best guess based on the evidence available. But over time, cracks began to form in this cosmic illusion. In the 16th century, a Polish mathematician and astronomer named Nicholas Copernicus challenged the deeply rooted belief that Earth was the center of everything. He proposed something radical, that the sun, not Earth, was at the center of the solar system, and that Earth was just another planet, orbiting around it. At first, Copernicus's heliocentric model was considered heresy. It contradicted both religious doctrine and the geocentric science of the time. But as more astronomers began to test and build upon his ideas, people like Galileo Galilei, Johannes Kepler, and Tycho Brahe, the evidence mounted in favor of a sun-centered system. This shift in perspective did more than just rearrange the planets. It cracked open a bigger question. If Earth isn't the center of the solar system, maybe it's not the center of the universe either. That thought was both terrifying and thrilling. Telescopes, still primitive by today's standards, gave us our first real glimpses into the wider cosmos. Stars were no longer seen as just pinholes in a celestial sphere. They were suns, scattered across an unfathomable void, and behind them, faint glowing clouds hinted at structures far beyond our reach. Fast forward to the late 18th century, and enter William Herschel, a German-born musician-turned-astronomer living in England. Herschel wasn't content to simply look at the stars. He wanted to map them. With the help of his equally brilliant sister Caroline Herschel, he undertook a massive star-counting project. Using a powerful telescope of his own making, William divided the night sky into 600 sectors, meticulously counting the stars in each one. The idea was straightforward. By measuring how densely packed the stars were in every direction, he hoped to infer the shape of the galaxy itself. His conclusion? That the Milky Way was a flattened, disc-like structure, and that our solar system was located near the center. That last part, though, turned out to be incorrect. Herschel didn't know about interstellar dust, which absorbs and scatters light from distant stars, especially near the galactic core. As a result, he underestimated how many stars were in that direction and mistakenly assumed the central region was sparse. But despite this flaw, Herschel's work was groundbreaking. He was the first person to even attempt mapping the galaxy from within it. And though his view was blurred by dust and limited technology, his efforts laid the foundation for everything that came next. In 1908, while working at the Harvard College Observatory, Henrietta Swan Leavitt made a discovery that quietly revolutionized astronomy. She studied Cepheid variable stars, which rhythmically brightened and dimmed over time. By analyzing over 1,700 of these stars, Leavitt noticed a powerful pattern. The brighter a Cepheid star, the longer its pulsation period. This relationship, now known as Leavitt's law, became a breakthrough in measuring astronomical distances. If you know how long a Cepheid takes to pulse, you can calculate its true brightness. Compare that to how bright it appears from Earth, and you can work out how far away it is. For the first time in history, astronomers had a reliable method, a standard candle, to measure vast cosmic distances far beyond our solar system. Leavitt's work became the foundation for later discoveries, including identifying other galaxies and ultimately helping us locate our position in the Milky Way. In the 1920s, astronomers were still unsure if the Milky Way was the entire universe. Then came Edwin Hubble. Using a powerful telescope, he found Cepheid variable stars in the Andromeda Nebula, what many believed was just a part of our galaxy. But when he measured the distance using Leavitt's method, Hubble discovered that Andromeda was over 900,000 light-years away, far outside the Milky Way. It wasn't a star cloud. It was a galaxy of its own. This discovery changed everything. The universe suddenly became much bigger, and the Milky Way became just one of billions of galaxies. And that raised a new, more focused question. Where exactly are we in our galaxy? Even before Hubble's galaxy announcement, American astronomer Harlow Shapley had already been working on this question. He studied globular clusters, spherical groups of ancient stars that orbit the Milky Way's center like a cosmic halo. By observing the distribution of these clusters with the Mount Wilson Observatory's 60-inch telescope, he made a critical discovery. The clusters weren't evenly spread around Earth. Instead, they clustered in one particular direction, toward the Sagittarius constellation. That told him something huge. We're not at the center of the Milky Way. The real center was far away, hidden behind clouds of dust. Shapley estimated that we were 90,000 light-years from the center. While not exact, it was a huge step in the right direction. Today we know we're about 26,000 light-years from the core, nestled in a small branch called the Orion Spur, between the Sagittarius and Perseus arms. By now you might wonder, why don't we just fly out and see the galaxy? Well, we've tried. Voyager 1, launched in 1977, is the most distant human-made object ever. After nearly 50 years, it's only traveled 0.02 light-years, barely a hair outside our solar neighborhood. Escaping the galactic plane would take us thousands of light-years, a journey we simply can't make yet. So instead of leaving the galaxy, we decided to map it from the inside. In our quest to understand the Milky Way's true shape and our precise place within it, no mission has been more transformative than Gaia. Launched in 2013 by the European Space Agency, Gaia is a space observatory with a remarkably ambitious task: to create a 3D map of over 1 billion stars, roughly 1% of the Milky Way's total stellar population. It's the most detailed survey of our galaxy ever attempted. But Gaia doesn't take ordinary pictures. Instead, it measures astrometry, the exact position, motion, and distance of stars, with unprecedented precision. This data allows scientists to watch how stars move across the sky, calculate their orbits, and trace where they came from and where they're going. So what has Gaia revealed so far? Thanks to Gaia, we've confirmed that the Milky Way is not just a simple spiral galaxy. It has a barred spiral structure with a dense, elongated core made of older stars. Gaia has also helped astronomers identify multiple spiral arms, including the exact contours of the Orion Spur, where our solar system resides. Even more astonishing, Gaia's data has uncovered evidence of ancient galactic collisions. It revealed that our galaxy has merged with several smaller ones over billions of years. One of the most significant discoveries is the Gaia-Enceladus event, a collision with a dwarf galaxy about 10 billion years ago that left behind streams of stars still moving through the Milky Way today. Gaia has also mapped stellar streams, dark matter distributions, and even starquakes, tiny oscillations on the surfaces of stars that reveal clues about their internal structure. And we now know that Earth, along with the entire solar system, is hurtling around the galactic center at a staggering speed of 828,000 kilometers per hour, completing one full orbit every 230 million years. A journey we're in the middle of right now. With more data releases planned through the 2030s, Gaia is not just mapping the stars, it's rewriting the story of how our galaxy formed, evolved, and continues to change. From Earth-centered myths to modern space telescopes, our journey to locate ourselves in the galaxy has taken over 2,000 years, and it's still ongoing. But what's clear is this: we are not at the center of the universe. We're not even at the center of our own galaxy. We are simply part of something vast, elegant, and mysterious, a tiny solar system in the quiet suburbs of a spiral galaxy. And yet, we figured that out. From a small blue dot, we've mapped the stars and uncovered our address in the Milky Way. That in itself is extraordinary. Now imagine this: if we've come this far by observing from within, what else might we discover if we could observe the galaxy from outside? And more importantly, what other galaxies might be observing us? Curious about how far alien civilizations might be, or why we haven't found them yet? Watch our next episode. Why can't we see evidence of alien life? See you in the next journey through the vast unknown.